So hello everybody, welcome to this new MoveX webinar. Today we will talk about the journey behind the development of a chip. I'm Stefano, in charge of the field application engineering team at MoveX, and today I'm here with Ilaria. Thank you, Ilaria, for being here. She is one of our first and most talented engineer in MoveX, and she will tell us everything about the development, the process behind the chip design. So just a brief introduction about MoveX before going to the topic. MoveX was born as an R&D division of Move Solution. Move Solution is a structural health monitoring company in Italy, but they needed more R&D, more innovation in their products, and so MoveX started as R&D division. But now we focus on IC design, and we have more than 50, 60 engineers daily working on IC development, microelectronics, and AI innovation. We have one mission: to change the way IC are designed and IC are developed. And the solution are here. One, our design services, and then our EDA toolchain. With our design services, we want to provide our customer, and actually also for our own chips, the best design possible, while also exploiting our EDA tool, Spaceman, which is an AI tool to completely speed up the process of IC design. So starting from the design service, which is the main topic of today's webinar, as MoveX, we have a great experience in many different technologies. The first focus was power devices, power products, in particular switching products like DC-DC converter, buck, and so on. So exploiting BCD technologies and other, but we can now make ASIC design for many different fields of application, like low power IPs, low noise architecture and structure, and many more. Moreover, we work also for advanced sensing products, exploiting high-end technologies like SPAD, in particular scaled CMOS technologies, and many more. So let's go to see how this is made in MoveX day by day by our engineers, and Ilaria will tell everything about this process. So thank you, Ilaria, for your presence here today.
Hi, Stefano. Thank you. Thank you for the introduction. As you were saying, today we will explore the chip development process, and we will go through its various phases, analyzing for each phase which are the most critical points and also the key professional roles involved, and also how they collaborate and interact to achieve the best possible outcome. So here on this slide, we can see a high-level overview of the workflow that is followed in chip development. We will go through each phase in detail, starting from defining the specifications, which act as basis for the feasibility study. During this phase, during feasibility, what we do is several studies to assess whether the specifications can be met and also the most effective way to achieve them. So once the feasibility is completed, we begin with the actual design process. And this process is carried out at the beginning at cell level, so focusing on the blocks that compose the chip. And we have three main steps. We start from sizing and simulations. So we take one cell, we size the block, and we simulate it. And if the results are okay, we can move forward to the layout phase. And then to the post-layout simulations. Also in this case, when the results of the simulations are okay, we can move forward. Otherwise, we have to go back to previous steps. So this process, these three steps are iterated until the specifications at cell level are met. And then when the cell level is okay, we can go to the top. So the top level of the chip is assembled, and then the exact same process, so sizing and simulations, layout, and PLS, the exact same process is iterated until also the top level specifications are met. Top level simulations are generally very long and also quite challenging to manage. So it is important that inside the team we define subset of scenarios to validate the top level performance. So after the design phase is finalized, we arrive to the final step, which is the tape out. During tape out, the chip is sent for production. And then after a few months, the first manufactured chip are tested during the ASIC testing phase. And during this phase, we assess whether any fixes are necessary for new versions of the chip. So one crucial aspect that spans the entire workflow and that should never be underestimated is the documentation. Why? Because every step must be carefully documented on one side to define all the technical details and to preserve them, and on the other side also to guide subsequent steps such as production and testing. So let's start by taking a closer look in the specification definition phase. Here, the key teams that are involved are on one side the application and sales department, and on the other side the technical department, which involves system architects, analog, digital, layout engineers, as well as the qualification team. During this period, these teams work together and collaborate to meet the customer request. What is essential here is to do first a market research on the state of the art and also on what is already on the market. But the most important point is to highlight all the critical aspects that are connected to the customer request. Why? Because the next step, which is the feasibility, is based on exactly on these critical points. The feasibility is carried out again by the two teams together, so technical department and application and sales department. And during this phase, a deep study is conducted on various aspects that includes pure technical design issues like first area evaluation, but also discussions about timelines, risks, cost processing, and so on. And the main goal of all this phase is finding an optimal trade-off between all these factors and ensuring high service quality for the customers. So once the feasibility is completed, the actual design phase begins. It involves primarily analog and digital engineers that are supported by the layout team. This phase is for sure the most critical and most delicate, most time-consuming, time-demanding, and it also depends on how challenging are the specifications, and also it depends on the designer experience. So it's really complex and time consuming, and this is a key point to keep in mind. And during this phase, the main goal is that all the specifications are met in all the discussed scenarios. So during this period, all the blocks are sized and simulated. Depending on the requirements and also on the state of the art, it may be necessary to study and search some new solutions and some innovative solutions. But what is really important to keep in mind is that if we use new structures that have never been used, that have never been tested at silicon level, so that are not silicon proofed, the design complexity increases and also the risk level. So when a cell is ready from a design point of view, it moves to the layout phase. In this stage, the layout engineers manage the component placement and routing, and they are supported by the designers who worked on the blocks, because they have to highlight the critical points and also to mark them clearly, like, for example, with notes on the schematic. Here, the key challenges are, first of all, the area constraints that have to be respected. Then we have the identification and routing of critical nets, such as band gap voltage or, in general, voltage references that should never be routed near to aggressive nets like clocks or, in general, switching signals. Then we have the routing of critical paths that, for example, require a low equivalent impedance or low parasitic capacitance to other nets that are near them. Also, matching structures are really important to handle, and I'm talking about, for example, current mirrors or differential pairs in op-amps. And then we have electromigration, which is a phenomenon where high current densities cause metal degradation over time. So this phenomenon has to be taken into account and has also some related design rules that must be followed. Okay, so when the layout of a cell is completed, the designer can proceed with the post-layout simulations. The goal here is to validate all the specifications again, but incorporating the extracted parasitic components in the layout view. Since post-layout simulations involve the larger netlist and can be really heavy and also really challenging to manage, they are typically performed in a subset of the previously analyzed scenarios, and we focus on the worst case that have been highlighted during the pre-layout phase. A crucial step here is the comparison between the pre-layout and post-layout simulations results, and also the collaboration between the designers and the layout team that have to work together to identify critical points in case some discrepancies between pre and post-layout results arise. Okay, so once the actual design phase is finalized, so we have the chip that is ready and all the specifications are met and so on, we can go to the final step, which is the tape out. During the tape out, the layout engineers finalize and send all the masks detail to the foundry team for the development of the chip, so for the production. The tape out is divided in two phases. We have the active tape out, in which we finalize and we send the layout of the masks that are related to active layers. And then, typically a few weeks later, we have the metal tape out, during which we finalize and we send the layout of the interconnection layers. Sorry, I have some issues. Okay. Okay, sorry. I don't know why. Can you hear me?
Yes.
Okay.
Yes, we hear you. We still
Sorry?
see the out slide. I don't know if you want it.
Okay. I don't know.
Okay.
I have themes that pop up. Okay, so what I was saying is the metal tape out. So during this phase, we finalize and we send the layout of the interconnection layers that are that define how the different components of the chip are connected. So now we are in this phase, so we are waiting for the chip to come back from the foundry, and when the first chips are ready, the foundry sends them back and we can begin the ASIC testing phase. During this phase, the application and test engineers perform and validate all the requested tests, and they are also supported by the designers who have followed the entire chip development. The tests can be for system level requirement, but also tests as for like qualification process, for example, for chip that are used in automotive or industrial systems. Here, the using of the ATE and in general the of testing equipment is required. And the goal is that based on these results, we can evaluate whether we need some fixes for future versions of the chips. These fixes can involve bigger changes like for changes in active masks, or in some cases only in the metal interconnection layers. So this concludes the high-level analysis of all the chip development workflow. What I've just presented is a standard workflow, and it is a really slow process. As I mentioned, in particular, the first phases, so the topology selection and the initial sizing are quite time demanding and quite complex, and really depend also on the designer experience. So these initial steps can be standardized for basic cells such as LDOs or current mirrors or op-amps. So it is really important to highlight that there is potential for innovation in such a flow, and this is the idea on which our R&D team start to try to answer the question, where can we accelerate the process? And so this is how Spaceman was born. Spaceman is our platform that is designed to automate part of the some steps of the design process flow, and to automate some steps of the design process flow using the AI, because Spaceman can give us like a schematic view of an IP, and to also to optimize the sizing of this IP. So now I handed it over to Stefano that will explain us how Spaceman works and its main features.
So thank you so much, Ilaria, for your explanation. I just remember that this webinar has been recorded, so you will find it later on our website. And I just give you a couple of more information about Spaceman, which is our AI-driven EDA tool we have developed to completely enhance and speed up the process of IC design. And here we have the analog design workflow that Ilaria well explained us, and Spaceman is exactly working in cell-level design. Cell-level design, as Ilaria explained, is one of the most time-consuming steps inside the analog workflow. And with Spaceman, we can completely boost the process of sizing, optimize, and simulate the cell. Spaceman can completely autonomously size and optimize the cell and give us a verified cell view schematic for every analog IP and basic blocks we can use to then make design in a more efficient way. So if you want more information, detailed information on the Spaceman, we have the last webinar from MoveX on our website called How AI is Transforming the Future of Electronic Design, in which you can find many more information about our Spaceman tool. And so thank you so much for your attention during this webinar. If you have any question, you can write down them in the Q&A box here, or left the question at our webmail, info@movex.ai. And let's see if we have some question here. I'll wait some minutes to see if there are any. So, okay, we have the first question for Ilaria. We have this question: how long does it take to make the entire process from draft to tape out, and then also testing and later to the final product?
Okay, so the duration of the entire chip development process is not fixed, so it can range from several months to like over a year for just one tape out. It depends on various factors, such as the technical complexity of the project and the level of their use of previous chips, but also on the number of the resources that are involved, so the number of the resources of the team, and also their work experience, because the experience will affect how quickly they handle both the design and then the issues that can arise during the project. So it is not fixed. It depends on several factors, but in general, what I can say is that from the early stages of a new project to the final release on the market, so when the chip is ready on the market, it can take several years because multiple tape outs may be necessary from the beginning, so to the from the first version of the chip to the final one.
Okay, so thank you so much, Ilaria. I see we have also one more question. This is related to Spaceman. I'll ask the question to you in any case, since it's related to how you use Spaceman in your daily work. And the question is exactly, how does Spaceman help you in this process of designing? How do you exploit this software in a practical way?
Okay, so as we were saying, the most time-consuming phase in all the chip development process is for sure the initial stage, so the topology selection and then the first sizing of the blocks, which also depend a lot on the designer experience. So what does Spaceman do? Spaceman uses the AI to handle these initial steps in just few minutes. So based on the specifications, on the requirements of the user, Spaceman suggests you the best architecture and it optimizes the block sizing. Then it will go in Cadence environment to do a first verification to ensure that the required performance are met. So this means that in few minutes we have an IP ready to be used in the design, and that also that have also specification guaranteed. Then I would say that along with the schematic and the symbol view, Spaceman provides you also the test benches that have been used to test the API. So it helps us not only during the design phase but also in the simulation process. So the main goal of all of these is to help designers to manage to save time on the development of building blocks, of fundamental building blocks. I was saying like LDOs or current mirrors or so on, allowing them to focus more on what is really new and innovative.
Okay, wow, that's a huge step forward in enhancing the design capabilities of our team. So I see we have one last question. It's more personal, but I think very interesting, since I presented you as one of the first designer in Move and one of the most talented, and that's sure. But the question is related to your career, and they ask, what has been your career path? How you move in how you moved inside Move?
Okay. Okay, yeah. I started my career inside Move as an analog designer, and I had the opportunity to work on different projects, both on the development of IPs for external customers, but also on projects that in which the entire chip design was managed internally within the company. So I had the opportunity to grow a lot and to learn, but not only from a technical perspective, but also in terms of project organization and team management. And so now I am the chip leader of a project that will last a year, since now, at least a year. And this role is, I would say, quite challenging, because it is the first time that I'm deeply involved in development phases that I previously knew only at a high level, because every designer, in my opinion, should know, at least at high level, all these phases that compose the chip development process. But if you are just like a designer, you can know the phases in at high level. Now that I am chip leader, I have to know, to understand everything in detail in every phase. So it's not so easy, but on the other side, I have to manage the work of the team to achieve the best possible outcome. So it's quite challenging, but it's also really stimulating, because it gives me the opportunity to expand my knowledge. And I am also really lucky, because in the company I have colleagues that support me and that have experience in this role. So I am learning a lot also from them.
Okay, thank you so much, Ilaria.
Thank you.
We quite run out of time, so we will surely answer all questions at the mail I tell you before. And again, you will find the webinar on our website. So thank you so much again, Ilaria, for all your explanation, and thank you to everyone here at the webinar. And see you next time on the next webinar in the future. Thank you.
Bye bye. Thank you.
Bye bye.